Jan Christian Lewitz. He's representing the advisory board for the Institute for Solid State Nuclear Physics in Germany. He'll speak about the dual fluid reactor.
So good morning. Yesterday there was a statement: phase out of nuclear will mean increase of use of fossil fuels. That's not true. Why? You know, the green NGOs have forced the phase out in nuclear in Germany, and now they try to force the phase out for coal. So Germany will neither use nuclear nor fossil. So it's good for all of you because we will be dependent on your electricity from around the other countries. And well, that's black German humor, but that's the only way to survive, and I hope it will not come true, but okay, the worst case. Topic is now the dual fluid reactor. Okay, you have a sketch here. You see the dimension of the core is 3 by 3 by 3 meters. We will have some more details later on. It is from the Institute for Solid State Nuclear Physics. If you check the site, you will find the people, and on the next, this is the people in the core. We have the main scientists, and around we have the advisory board from some universities and from industry. Short brief history about nuclear. Okay, why do I show this? That's not very interesting, but when we see the red lines down, it shows that all we speak about now has been already investigated long time ago. The only thing that we have is that all the so-called generation 4 nuclear reactors, they use solid fuel rods, and the molten-salt reactor doesn't do that. That is the very big difference, and we have heard about the advantages of the molten fuel before. Okay. And this is more detailed sketch about the DFR design. We have in the fuel loop almost steady state molten salt. This is really the big difference to all the other molten salt reactor designs, because we don't use the molten salt for the coolant. For the coolant we have a lead in a lead coolant circuit, and it means that the molten salt with the fuel can stand in the core for a long time. We have very high transmutation rate. We don't lose any transmuted isotopes when we bring them out for coolant and they decay, because then they stay in the core and they have one neutron absorption and second and third. So we have this chain to destroy the plutonium and the other minor actinides, and we have the very high transmutation rate there. Okay, and we only have a very tiny amount that is taken out to the online cleaning unit, the pyrochemical processing unit. I think maybe yesterday I thought we shouldn't use processing but cleaning, because processing, everybody thinks about Purex, and we don't want that. So I will suggest we change the name maybe. We have heard about the melting fuses. That's always for the molten salt reactor. If we have a kind of too high temperature, reactivity increase, and we have heard about the negative temperature coefficient already. I will show later. And what is the important information here is it was patented in 2011 already. Okay, unfortunately you can see the development is not so fast, because it's already 7 years ago. And it's also the problem that everybody has here. We have to open the wallet and collect some money for more research outside the office. Computer work is okay, but laboratory costs some more money. Okay, some more details. We have tiny tubes here with the fuel, and you see the small, tiny green arrows show low flow velocity, and the lead goes in and out. That brings the heat to the usage turbine or thermochemical processes, hydrogen production, and that's a big difference to the molten salt reactor. Okay, what is more, from the PPU we get all these short-lived fission products we sort out, and they are stored on site for decay. Most of it will be decayed in the first 100 years. 90% will be below the radioactivity limit of like this table or you and me, and we can give to the public, to the industry as valuable materials. And the remaining 10% will decay in 300 years. So 90% in 100 years, and the remaining 10% in 300 years. Okay, you see just as a sketch the undercritical storage tanks in the basement by gravity drain. Yeah, and it can all be, as it's very small, as you remember, this is 3 meters in the cube, and it can be underground, and only the conventional island will be on top, so all this is encapsulated, and it's very safe for external events, like airplane crash or others, or terrorist attacks, yeah, which is also claimed now from our environmental activists. Okay, something else, we have an operating temperature in design of 1000 degrees centigrade, which is a little bit higher than in the other molten salt reactors. Yeah. Okay, you have heard about the negative temperature coefficient. Yeah, I just repeat this, it's also here. It means that also we are very able to go the load following. Yeah. The extraction of heat on the secondary side, if you extract less heat, it will mean that the temperature in the primary coolant and in the molten salt will increase and the reactivity will go down. And the temperature will be kept. So it's very close load following. If we extract more heat from the turbine or the chemical usage, the thermal application, then the temperature will go down in the coolant and in the salt, and the reactivity will go up. So we have very instant load following capabilities, which could also be if it's required, load following for wind and solar. Okay, yeah, but if that's required, it can be done. Yeah, we have it here. Yeah, okay. Yeah, even hot standby is possible. Yeah, so that's just, it will maintain its temperature by itself, and we don't extract any energy. Okay. So that's the standard molten salt reactor core. Okay, we have a homogeneous core, and that's the same for both. And we have the heat removal by the salt that is in the molten salt reactor, and here we have the heat removal by the second fluid, which is by design for a dual fluid reactor, is the lead. Here the fuel is limited to salt, yeah, naturally. Here the fuel could be, now its major design is chlorides, but it could also be eutectic. It is another design, then you don't need to refuel, you don't have a pyrochemical processing unit, you just drop some fuel to compensate poisoning by fission products and the burning of the fission, of the fissile material. Yeah, so that would be encapsulated for a longer time, for several years, and then you take the reactor out. The standard design with the chlorine will mean we have the online cleaning, and thus the reactor will stay there and operate for a long time. Okay. Okay, we have seen about this. What is interesting here is the cost share. And usually we have in the standard light water reactor, we have this, the big part is the nuclear island. And the smaller part is the conventional island. This is different here. We have almost 50% we have in the conventional island. According to the current calculations, yeah, it has not been built, so we have to prove it. Yeah, that's the main thing I want to say. So, about efficiency, okay. The design allows a high power density. That's for all molten salt reactors. We need less material. Therefore, we can afford high quality materials, which are not used in light water reactors because the core is very big and the reactor pressure vessel and the fuel elements and like that. As we don't have it, we have a very rare little amount of materials. We can afford high quality and expensive material, yeah, because it doesn't contribute to the overall cost very much. I have to say we use the enriched chlorine 37. Yeah, there was yesterday from another design. It was they use a standard chlorine. We use a chlorine 37 not to waste any neutrons and not to have any additional radioactivity from the activation. Okay. Okay, high temperature I said, so this leads all to very efficient process and also the thermochemical hydrogen production and in overall lower cost for the plant and for the outcoming products. So it will be able to have a economic operation. Okay. I did speak about the materials already, okay. In other applications, these technologies are used, like in, we will show later, in the fractional distillation, I will come to that. So the materials are already available, like silicon carbide is used, also investigated for the pebble bed reactor. They try with the silicon carbide outer shell to replace by the non-activated carbon, the by silicon carbide. And refractory alloys are available on the market. You can buy them. Yeah, they are very expensive, but they are available in all kinds of. Question is if this could be done in 3D printing. That is under investigation also by one colleague here doing some research on that, because the high quality that is required currently is not available, but they are doing research there, and that would be another lecture, and that should be given by somebody else. That's not my topic. So the fractional distillation, what is the pyrochemical processing unit? That's very different from all the other designs. Here's an example for air, the fractional air distillation. You can have the same for crude oil. Unfortunately, I don't find for the Kroll process where it's used for titanium production, because the titanium production works also with the chlorine 3 and is temperatures of about 1,600 here. We would need temperatures up to 1,800 to get all the elements out. But it's the same principle, yeah? And it is for the high temperatures. I show on the next slide. Anybody that's interested can check on the internet. This is one example for titanium supply. It's long time. It is available, this process. Many steps are the same, and the core is the fractional distillation at these high temperatures for the chlorine 3. Yeah? So that's available on the market. It works for... we don't have the tons that are produced per year that are many tons per year. Yeah, so it just has to be adopted. Yeah, this is one of the core slides. Okay, why? I spoke yesterday and I was told don't focus too much on the waste issue because we don't have a waste issue. But as we Germans are crazy, and we are in the environment where the waste issue is, on the front in the discussion, and the government has the money now taken from the utilities, 23 billion euro, and they have taken away even now the spent fuel, so-called spent fuel, because we had a shift over of ownership from the utilities to the government, yeah? And for the bad spent fuel, they had to give the 23 billion. Okay, so the government has the money, and they have the 97% of energy in the spent fuel. So we hope maybe some people have an idea to do something about that, okay? And that's where it starts, okay? You have to do the chlorination, yeah, that's fine, that's not a problem. In the beginning, the mechanical disassembly is like in the old Purex process, and then you do the chlorination of the metals. Okay, so, and then in the first step, we do the partitioning, yeah? We do the partitioning, and with the PPU, then we have like 96% is uranium, and you can store, doesn't matter where you store non-nuclear material. We have 1% plutonium and minor actinides. We have 3% fission products. Okay, so the waste problem is reduced to 4%. If we don't do anything else than the partitioning, we have only 4% left. Now that's not so bad, huh? To reduce the size of the geological repository, that's the first step. I think that's good. That's good. If we still think we don't want a repository 1 million years, we are now from 100,000 years to safeguard it to 1 million years in Germany. Because 1 million is just even less understandable for the public than 100,000 years, yeah? No, that's really, yeah, that's the way, the figures are big, After Chernobyl, we had the picobecquerel that were counted in the salad. Because the picobecquerel gives a big figure. When you have some billion picobecquerel, it's a big figure, okay? And otherwise, it would have been maybe 5 becquerel. Okay, yeah, but what is 5? 5 is nothing. So, but some billion picobecquerel is great. If you use then, you can use all of this, yeah? Well, use mean you can use this, you can burn this. This is fissile in the DFR, and you will transmute the minor actinides, and you will, the long-lived fission products you will make to 4 short-lived fission products, and they go into the storage, and actually, that is what we want to go to get some of these 23 billion, hopefully. Oh, okay. Well, Arno, I have some more slides. Yeah, okay. We spoke about the external fuel cycle from the light water reactors, yeah? And 1% of the mined uranium is used in the standard fuel elements. And 99% is waste. Okay, well, yeah. If we count also the tails from the mining, yeah, I think the tails are not. If you treat the tails properly, yeah, if you have like the big vast hill there that emanates, yeah, then it's not so nice. But if you have the metal uranium, you can place it somewhere. It's used as a balance weight in air. 5 minutes, yeah, I will be ready, thank you. Yeah, okay, actually I have talked about all this, yeah, okay. Okay, energy return on invested. That's very, very interesting because there is a publication in the energy. It was peer reviewed and was now in the community is discussed. So that has a, you know, it has a kind of was recepted, yeah. And we look here. That is the so-called renewables. Okay, below 4, we have the energy return on invested. If we have a society working on that, it would mean we go back to wind and water mill efficiency. We can survive with that. But we don't have society we have now. And even, yeah, if this is current society, between 30 to 75, the pressurized water reactor, okay, yeah. And here's what it means. The energy you get out to the energy you give in. And it is including building the facility, mining and fuel production, and also the back end, the dismantling and waste disposal, yeah. So, yeah, okay, the economic threshold, what they say, and in the internet I write, you know, if you have to produce your windmill and your photovoltaic panel by electricity from wind and solar, yeah, and you are not allowed to use fossil or nuclear. You just have to use wind and photovoltaic and biomass to make your solar panel. Think about what would happen. It would not happen, okay. Okay, I skip this one. It just says we have even more higher factor that we have in the nuclear fuel when we use the fuel, okay, correctly, as we can do with the molten salt. And here you see where what I said about, we have the mining, we have the conversion, we have the enrichment, it's about 2/3, 3/4, almost 3/4. And we don't need that. We don't need that in the molten salt in the dual fluid reactor. Okay. Yeah, okay, this is just for the light water reactor, what, depending on where you get your enrichment, and it's based on nuclear or on fossil. Okay, and I also skip this one. And with the dual fluid reactor, yeah, now it looks like not much better here as for wind and solar, the 75. It's calculated in the papers that you have there, you can find that. It is calculated by 2000 energy return on invested, okay? People think we are making a joke and it's a comic, it's a Mickey Mouse, but it's in the documents and it is analyzed from the beginning to the end. You can look at that, you can check that, and there was no scientific showstopper for that, yeah? It's in the people that read it so thoroughly, and in the discussions it is accepted, but in the public it is difficult. Okay, I'm in the end now, yeah? 2 minutes, 1 minute? Okay, yeah, fine. Last slide. Okay, this is now, okay, as always, when the priest gives you what is in paradise, okay? This is our nuclear paradise. Desalination of water, very cheap electricity, petro products, steel production, and here is the synthetic fuel production. If you, for example, from the hydrogen you produce by a thermochemical process, you can later make the hydrazine because it can better be stored than hydrogen. And you can use an airplane propulsion. It was used for rockets, yeah. Some people say it's dangerous, but the danger is like gasoline, similar, okay? And you can fuel the car. It can be combustion car, so you can have like the combustion engine with the hydrazine, and later you can have the fuel cell car. So we have a smooth shift from combustion engine to electromobility, yeah? So, and that's also a request we have, electromobility, and that's it, you know? Okay, I hope, yeah, support is always welcome. I have my little wallet here, so if you want to contribute a little bit, I will open it up. Okay.
Any questions?
You are using lead to cool your core
Yes.
inside. but I suppose your lead is becoming at the end radioactive also. So you.
Well, lead is always going back to the lead, you know. It's all all the chain, nuclear chains end in the lead. So lead almost is transparent for neutrons. You have very little absorption. You have almost no moderation. And in case you have like neutron absorption in the lead, what comes out goes back to the lead.
How big is the reactor in terms of capacity?
Yeah, so this was standard design. It can be from 300, maybe even smaller, but I think not below 100. The original idea was to replace the 1.5 gigawatt class. Yeah, but it can be for process heat applications. There are discussions with other countries that are interested to replace coal-fired plants, and they have like they have the heat exchanger of 300 megawatt because that was the coal, and they want to replace by nuclear. So then it would be 300. That's also that's possible.
What is the vapor pressure of your plutonium chloride at 1,000 degrees C?
Well, the boiling temperature is far above 1,000, so it's almost atmospheric. Yeah, that's okay. I didn't speak about that. We had yesterday when we have a leakage, if there is some hole somewhere, we saw this. The salt is poured on the plate. It's freezing. So that's the other. But the pressure, we have almost pressureless system. We don't have any stored energy there. We don't have any vapor explosions possible. So the plant cannot be destroyed. We just can have contamination because if all drains out and doesn't go to the drain tanks there, then the plant is contaminated. But it's not for the environment outside. Yeah, it's just we lose our investment there. But that's the worst case. Yeah, we don't expect that. But even you have to find the case that you have a catastrophic release inside the building. That's the only catastrophe inside the building. We don't have any major release to the outside. Yeah, some fission gases sure will go out, but it will not lead to any need of evacuation. Yeah.
My point was more that vapor pressure, even at 600 degrees C, of plutonium chloride is enough to cause challenges in the off-gas system. And you're up to 1,000, so I'm wondering how much plutonium are you have coming off as gas? And how are you?
Okay. I will check that as a question to my colleagues. I cannot answer that now. Okay. Vapor pressure plutonium chloride, yeah?
Yeah, hi. Two questions actually. What is the design lifetime for a dual fuel reactor? And the second question is the generation for people working on lead consider that the abrasion of lead on materials is a very big problem, and how do you solve that?
Yeah. Well, the idea is that these high-dense ceramics like silicon carbide and the refractory alloys will allow a long time operation, okay? That will not only be in single years, but more than 10 years, yeah? We have now planned, as all these theoretical calculations for neutronics and for thermohydraulics have been done, we need to do experiments. And that is what we are now. We had some governmental money for partitioning because that is allowed in the small parts of the repository searching. We hope to get some more money to do some laboratory testing. And as I hear, there are some other institutes doing that. Maybe I think we should have some cooperation there. So again, this is something we have to investigate, but we are quite confident we can solve that.
Yeah, sorry, what is the design lifetime?
Let's say, if I say 10 years or 15 or 20 years. Okay. Yeah.
Do you consider yourself to be part of the Molten-Salt reactor community, or do you think you're being hybrid? So you are, because I understand that the last presentation said that he assumed that most of us were part of the Molten-Salt community in this room, which is not necessarily the case. So what I wanted to know is, given the fact that there is an urgency for the planet, excuse me, but Molten-Salt reactor, it's like in 15 years or 20 years, which is probably not the case for other innovative reactors. So it's a very good question that I asked you, knowing what is your time frame. So you think maybe it would be operational in 10 years?
Well, a demonstrator, the current plan says the demonstrator could be, if there's some sufficient funding, could be in 5 years. I'd say that's too optimistic, but that's in the plan. No, we are in this regard part of the Molten-Salt community, because a lot of what we do is within there. There are some differences, yeah, with the coolant, but all the other things are the same, yeah, which has to be investigated. Material issues like the volatile issues, the gases treatment and like that, it's all the same. So yeah, no, we are not out of the Molten-Salt community, but we have some differences. Yeah? And back to the question of the lifetime, yeah, the core could be exchanged then later. It doesn't mean that all of the plant is the lifetime end is when the core has the lifetime end, yeah? So not.
All right.
Instead of that, you think your time frame is going to be shorter than the rest?
I fear not, no, yeah.
Okay, let's thank the speaker again.
Oh, yeah, okay.